The pilots of a turboprop airliner face a nightmare situation over Papua New Guinea.
Mayday, mayday, mayday. Double engine failure and we're making an emergency landing.
This crew lose both engines at the same time. There is only really one outcome.
Investigators quickly discover clues in the wreckage.
Landing gear's up.
The flaps are up too.
They weren't configured for landing.
Something in the cockpit voice recording
Amplify what's left.
Well, there it is.
reveals a potentially deadly flaw in an aircraft used around the world.
We wanted to make sure that the 1,000 aircraft that were out there were operating safely.
Airlines PNG Flight 1600 soars 16,000 feet above Papua New Guinea's Finisterre mountain range.
We're at cruise.
Australian Captain Bill Spencer is an experienced flight commander.
Cruise power is set.
New Zealander Campbell Wagstaff is the first officer on today's late afternoon flight.
Both pilots were with PNG for about a year. The captain had very good experience. He had about 18,000 hours of flying time. The first officer was also very experienced with just shy of 3,000 hours flying experience himself.
One flight attendant looks after the comfort and safety of the 29 passengers on board. Most are parents heading to their children's graduation at Divine Word University at Madang. PNG Flight 1600 is midway into a 30-minute flight to the town of Madang on Papua New Guinea's north coast.
How's the arrival time looking?
17 after the hour, right on time.
The pilots are flying manually today because their autopilot is inoperative. They're at the controls of a twin-engine Bombardier Dash 8, well suited to carrying passengers around the Pacific Island.
The airplane is able to operate in and out of short runways, unprepared runways, oftentimes in smaller communities where the facilities required to operate a larger passenger aircraft wouldn't be available.
Two Pratt & Whitney turboprop engines power a plane that's nearly 23 years old.
The Dash 8 is one of these airplanes that's become timeless. It's still operated by airlines all over the world. As some of the major airlines upgrade their airplanes to more modern jet aircraft, the Dash 8s find a new home with other airlines because they're always in high demand.
Charlie Bravo nearing Madang. We're coming through it.
You hear that?
40 miles from Madang, the pilots get an update on the weather ahead. A storm is building near their destination.
I'll take us around it, all right?
Good idea.
Turboprop aircraft cannot fly as high as a jet airliner can, which means they can't go over a lot of the weather they may experience on their flight.
Madang Tower, Airlines PNG 1600. We're diverting slightly to avoid weather.
PNG 1600, Madang Tower, diverting, copy.
Captain Spencer navigates around the storm.
The captain is trying to avoid clouds, which is normal. You want to give your passengers a smooth ride.
But 38 miles from Madang, the crew still can't see the airfield.
I'm going to take us down.
Copy.
At a major airport, there are typically procedures in place that we can fly that will bring us through the clouds and point it right at the runway. Oftentimes, at more remote airports, these procedures do not exist. So we have to descend below a layer of clouds. Once you're below a layer of cloud, you can visually navigate to an airport and conduct a safe approach and landing.
The crew advises the tower of the revised flight path.
Madang Tower, PNG 1600. Passing 13,000 on descent. Estimated Madang, 16.
PNG 1600, Madang Tower. Say again your level?
Passing 12,300.
Roger. Runway 07. Rain showers overhead, passing from the east.
While Captain Spencer makes a sharp descent through the clouds, the plane picks up too much airspeed.
Aerodynamically, flying overspeed by a couple of knots is not really a big deal. Think of it like driving a couple miles per hour over the speed limit in your car.
Airspeed, mate.
Got it.
There are several ways to slow down the airplane. You can increase the pitch of the airplane, and this will reduce the airspeed as the airplane aerodynamically slows down. Additionally, you can reduce the power to the engines.
What have we done? I don't know, mate. I don't know.
An ear-splitting sound makes it almost impossible for the pilots to communicate.
It would be overwhelming. There's loud noises that you're not familiar with. There's smoke. There's warnings being generated by the airplane, and it's all happening at once.
It's overspeeds. Overspeeds. It looks like double propeller overspeeds.
First Officer Wagstaff notices the propellers are rotating too fast. The plane is in a precarious state.
There could be control difficulties. There could be engine damage. And in severe cases, there could be engine failure.
What have we done? It's overspeeding. Number 2 is shut down. I can't hear you.
The crew would have a very difficult time cutting through the noise and trying to identify the initial root cause of these problems.
Finally, the deafening sound dissipates.
You got the left side working?
No.
Okay, we got nothing.
Both engines have failed. The plane is descending fast.
This crew was faced with a scenario where they lose both the primary and the backup system on both engines at the same time. That backs the crew into a very difficult situation where there is only really one outcome: a forced landing.
A forced landing means the pilots have no choice but to land immediately. 16 miles from Madang Airport, Captain Spencer turns the plane back towards the coastline. He needs to find a safe place to put the plane down.
Tell the tower.
Madang Tower, mayday, mayday, mayday. Airlines PNG Flight 1600. Double engine failure and we're making an emergency landing.
Confirm you are able to make it to the field.
The optimum scenario in a forced landing would be gliding to an airport. Failing that, the next best choice would be landing close to a town or city. This may increase the odds that the airport fire rescue services can attend to both the aircraft and its passengers and crew.
But no such options exist.
Brief him that we're gonna ditch.
Negative, negative, negative. We'll probably be ditching.
A ditching is a forced landing that has to be made in open water. It is the last choice for pilots if an alternative exists.
Flight 1600 is rapidly losing altitude, and time is running out.
Look there, a river.
From altitude, a riverbed may look like a long, safe area to land the airplane in a forced landing situation.
I'll get as close to the mouth of that river as I can.
Airlines PNG 1600. We'll be ditching on a river.
Confirm location.
Controllers need a location so they can send help.
Not sure the name of the river.
The lives of the 32 people on board are at risk.
Pilots will remain focused right until the very end. A pilot will not stop fighting to save their airplane.
Want me to shut both engines down?
Yeah, shut everything down.
Shutting down the engines prior to a forced landing off-field could help slow the spread of any post-crash fire that may develop.
Flight 1600 is now a glider. The Dash 8 is only a few hundred feet above the ground.
At a certain point close to the ground, the pilots have to rely on the decision they've made and hope that it was the right one.
Brace! Brace!
Seconds from touching down, Captain Spencer sees a deadly hazard.
Boulders!
All you would have is your eyeballs. What you see from 10,000 feet and 5,000 feet and 500 feet may look different as your depth perception increases as you're getting closer to the ground.
200 feet from the ground, Captain Spencer tries to avoid huge boulders on the riverbed.
Brace! Brace!
The only option is the river bank. Airlines PNG Flight 1600 has crashed into bush near the mouth of the Gwabi River. 28 people are dead. Just one passenger and the 3-member flight crew survive.
It was a dry riverbed, so the aircraft broke up into many parts, and then there was a post-impact fire, which destroyed a lot of the evidence.
The Papua New Guinea Accident Investigation Commission rushes a team to the scene and calls in help from other countries.
I was pretty keen to get the lay of the land and see what this accident site looked like, and also get boots on the ground.
Eric Blankenstein from the Australian Transport Safety Bureau is among the first investigators at the scene.
My first impressions were that this was an incredibly large and difficult site to work, and we needed to prepare logistically to get this job done.
The length and shape of the wreckage field indicate how the plane came down.
300 meters long.
It spreads out from the point of impact.
If you have this long distance and it has this V-form and wreckage trail, it means to us that it's a low angle of entry and also high speed. So straight away we'll be able to get the impression that this off-field landing was particularly fast off-field landing.
Let's see how they configured the plane.
Normally, when you're doing a landing, including an off-field landing, you would have the flaps down so you can effectively land the aircraft slower. The landing gear configuration also, you would expect them to be in the down position to soften that blow of impact.
Landing gear's up.
Blankenstein finds the landing gear actuator in the raised position.
The flaps are up too.
They weren't configured for landing.
Without the flaps and landing gear deployed, the plane would have hit the ground at high speed. But what triggered the crisis is a mystery.
This is the left engine.
The left engine had separated from its wing and broken into two sections.
Did the turboprop engines play a role?
Immediately my attention was drawn to some issue to do with the engines, although we don't try and narrow down our focus too quickly.
Not a lot of rotational damage to the props.
They can tell from the condition of the propellers that very little power was coming from the engines.
Were the left props feathered?
I'll check.
If an engine fails, the pilots need to adjust the pitch of the propellers so they don't create drag. It's called feathering.
Pilots generally don't feather propellers of aircraft unless there's an engine problem. If you feather a propeller, you no longer have propulsion to your aircraft.
The left props were feathered.
Did you check the right props?
Yes, they're feathered too.
When we identified that the propellers were both in the feathered position, immediately we were of the understanding that there was an issue with the engines themselves.
We're gonna need these airlifted out of here.
I'll arrange it.
We're able to airlift those out with a helicopter to Madang and then transport the engine sections to Port Moresby, where we could do a full and thorough examination of those engines themselves.
I've got the data.
David McNair from the Transportation Safety Board of Canada joins the investigation.
We had the notification from Papua New Guinea that the Dash 8 had crashed. Of course, since the aircraft is manufactured in Canada, that requires our involvement.
Can we hook this up, please?
They focus first on the flight data recorder.
The information about the engines on site was limited. The real evidence you're looking for is the flight data recorder. A lot of these parameters will tell you when the engines did what and how it happened.
Check this out.
Investigators learned that 28 minutes into the flight, the rotations per minute, or RPMs, spiked to 1,500 on both engines. It's the highest level the FDR can record.
Well, that's not normal.
So the normal operation of the propeller in the air is about 900 RPM to 1,200. During the flight, they went above 1,500.
Double propeller overspeed.
Investigators discover evidence of a frightening engine condition called a double propeller overspeed. Overspeeding propellers can destabilize the turbines and cause catastrophic damage if pilots don't catch the problem soon enough.
You want the engine driving the propeller. You never want the propeller driving the engine. And that condition is where you see this overspeed. Both engines saw a propeller overspeed condition, which is extremely rare.
Could the double propeller overspeed have caused the crash of Flight 1600?
If the engine overspeeds fast enough and hard enough, the parts will break, and then you don't have control of that engine anymore.
We need a closer look inside those engines. Wow, look at this.
Damage to the turbine blades in Airlines PNG Flight 1600's left engine provides unmistakable evidence.
It's corn-cobbed.
Right.
Corn cobbing occurs when the speed of the propeller is so fierce that it causes all the blades in the turbines to shear off.
The blades physically look like they've been chewed out of the power turbine. So it gives the corn cob look. And that's a feature by design that about 145 or 150% over speed they shed.
Corn cobbing is a protective measure that prevents the turbine blades from spinning quickly enough to tear the engine apart.
Have a look at the right.
Well, the right looks perfectly okay.
Unlike the left engine, the right turbine shows no obvious signs of overspeed damage.
The left engine had shed its turbine blades, whereas the right had not.
Something completely different happened to the right engine.
The right engine was feathered, but mechanically looking at the turbine itself, it appeared to be undamaged.
We had assumed that both engines had been damaged during the overspeed, but clearly the right engine didn't see as much distress as the left. It certainly raised questions going forward with the investigation.
I can't figure it out.
Regardless, wouldn't the protective systems have kicked in?
Good point.
There are 3 protections designed to prevent each engine from overspeeding: a propeller control unit, an overspeed control unit, and a backup system.
Both of these propellers going above the maximum so rapidly would have to bypass those 3 systems.
Did the engine protection systems fail?
As in most investigations, you start looking at what are the reasons why this was possible. Was there a system out there that would prevent this from happening? The answer is yes. There was a system, there was a design.
Test results.
Investigators analyzed tests performed on the protection systems for Flight 1600.
No data on the right engine.
Inspections performed on the right engine protection systems are inconclusive due to post-crash fire damage. Investigators send them to the manufacturer for deeper analysis.
Maybe they can figure out what happened to it.
What about the left?
The left engine isn't as badly burned, and inspections provide a critical answer.
All 3 protections were operational.
If the protection systems on the left engine were working, why didn't they prevent an overspeed and eventual corn cobbing?
Bypassing 3 systems of protection at the same time would be a statistical improbability. So we knew that there was something else involved in these propeller overspeeds.
Let's see what the pilots have to say about what happened.
The team reviews transcripts of interviews with the 2 pilots.
You obviously build a list of questions you want answers to. What was in your mind's eye at that point in time? Were you aware of why the propellers oversped? You know, what were your actions at the time?
Captain said there was a lot of cloud cover on approach.
What else?
I'm gonna take us down.
Copy.
Then out of the blue, the airspeed warning started to sound.
As Captain Spencer started his descent below the cloud, a warning sounded, alerting him that the plane was going too fast.
What did he do?
He said he raised the nose, pulled back on the power.
Sounds right.
Agreed.
Airspeed, mate.
Got it.
If you get a speed warning, you need to slow down. The first and most obvious is being to reduce the power. Think of it like taking your foot off the gas pedal in your car.
The captain's testimony doesn't provide any new leads for investigators.
What did the first officer have to say about the airspeed warning?
Get this. He says once the warning sounded, the captain yanked the power levers back quickly.
First Officer Wagstaff's testimony adds a crucial detail.
And the co-pilot particularly indicated that the power levers were brought back very quickly, and then the problem happened right after that.
What have we done?
His instinct to pull the power levers back was correct. But did something happen when he pulled them back quickly?
Maybe he pulled them back so fast they went all the way into ground beta mode.
The power levers on the Dash 8 have 2 settings, flight mode and ground beta mode, used only when the plane is on the ground.
You need a mode where you can taxi the aircraft and have direct pitch and power control over the propellers themselves. It allows you to operate the aircraft more simply on the ground.
Pilots are trained not to put the plane into ground mode while airborne.
The only time to be in the ground range is when you're on the ground, when you're starting the aircraft, when you're maneuvering the aircraft, when you're taxiing the aircraft.
If you put the plane in ground mode mid-flight, would that disarm those overspeed protections?
Let's look at the flight manual. Well, listen to this. If pilots put the plane into ground mode mid-flight, it would have disabled the protection systems.
If he's pulled the power levers back rapidly, you're now into no man's land. You're on the precipice of disaster because you have no propeller control.
So this is a case of pilot error then?
Maybe. But maybe not. Don't the power levers have a protective gate between flight mode and ground mode?
That's correct.
A mechanical stop, or gate, prevents pilots from moving the power levers into ground mode by mistake. Triggers on the power lever lift the gate, allowing movement to ground mode.
You have to physically move your hand around the front of the power levers to reach those two small tabs, and you pull them vertically up, and then you can move it back. But it's certainly nothing you would want to do in the air.
Investigators need to find out if the mechanical gate was working properly on Flight 1600.
It looks like some of the pieces survived the crash. The trigger springs are burnt from the post-crash fire, but they're still good.
Did the power lever triggers fail, allowing the propellers to overspeed?
The wreckage information was limited. Quite a bit of stuff was destroyed by the fire, but the things that were there were analyzed. In this case, one of them was the trigger spring.
The spring is supposed to hold the power lever triggers in place.
You've still got resistance.
The spring was working correctly, and the triggers were working as designed. And so we could see that in the inspection.
If the triggers were working, how easy would it be for the captain to lift them and pull the lever into ground mode?
We decided to look at the human factors aspects of the protection system, trying to ascertain how much you needed to lift the triggers to take it below the flight idle gate.
So, I ran a test on the levers. First, I tested the levers to see how well the gate works. I didn't touch the triggers. The levers came to a full stop.
The gate worked as designed.
Correct. So then, I did it again, this time quickly.
Blankenstein simulates the captain's physical reaction to the airspeed warning.
Without even trying, I pulled the triggers.
That shouldn't happen.
The team discovers how easily the pilots could have put the plane into ground mode by mistake.
We noted during testing of the power levers that if you were moving the power levers back quite rapidly, we could see how it would be quite simple to actually inadvertently pull the triggers without even realising that you'd done it.
The pilots only needed to lift the triggers 6 millimeters for the levers to move past flight idle and into ground mode.
I don't think anybody who flew the airplane at the time was aware that a 6 millimeter pull of one trigger could cause both engines to go into propeller overspeed condition.
But did Captain Spencer actually do what investigators suspect?
We're 4 minutes before they crash. Let's start.
Investigators listened to the cockpit voice recorder to confirm their theory that the captain pulled the power levers into ground mode.
I'm going to take us down. Copy.
They hear the captain begin an early descent to avoid bad weather.
The cockpit voice recorder records the voices of the people in the cockpit, but it also captures all the noises, and the noises can be very useful for analysis.
Soon after, the airspeed warning sounds. It fits with what the captain told investigators.
Airspeed, mate.
Got it.
Whoa. That is a wall of sound.
It's the sound of the propeller overspeed.
It's very, very loud because the propeller tips are breaking the speed of sound, and so you get these really, really high sonic booms back and forth, a lot of vibration, a lot of noise.
Go back 5 seconds. I thought I heard something before the propeller overspeed.
As they listen to the cockpit conversation,
Airspeed, mate.
Got it.
a tiny sound catches the team's attention.
Did you hear that?
I heard something. It's hard to tell what exactly. Can you delete the sound of the props?
Investigators sift through the layers of sound in the cockpit.
Try losing the sound of the alarm as well.
Okay, amplify what's left and let's have a listen.
There it is.
Buried deep within the noise of the cockpit, they discover what they're looking for.
This clicking sound just before the propeller overspeed was perhaps the pilot in command pulling the triggers upwards into the ground beta range.
Now we're getting somewhere.
Right after the click, they hear another critical sound. It's the beta warning horn, initially drowned out by the overspeed noise.
The beta warning horn sounds when you take the power levers into the ground beta range. It was intermittent and it was very difficult to hear above the sound of the propellers themselves. So we could hear these little tweeting sounds on the cockpit voice recorder that indicate that that was the case.
Airspeed, mate.
It's definitive proof that confirms the investigators' suspicions. The captain put the plane into ground mode mid-flight, causing the propellers to overspeed.
The flight manual states specifically never to go below the flight idle gate. It's prohibited, as a matter of fact.
But if it's so easy to do, how come it hasn't happened before?
That's a good question.
Was the crash of Flight 1600 caused by an unlikely pilot error? Or was there a deficiency with the Dash 8 that allowed it?
We need to find out whether we have a problem with the fleet. We wanted to make sure that the 1,000 aircraft that were out there were operating safely.
This can't be the only case.
Investigators look for evidence of other pilots who have made the same mistake as the crew of Flight 1600.
Yes. Really?
About 2 months after the Madang accident, there was an incident involving a Dash 8 where the propellers had oversped.
Right, thanks. It's happened again.
What's happened?
An incident just like Flight 1600 just a few days ago.
The team learns about another crew in Australia that put a Dash 8 into ground mode mid-flight.
In that particular case, the first officer had their hand on the power levers and they experienced an updraft followed by a downdraft and inadvertently gripped the triggers of the power levers and moved the power levers below the flight idle gate.
Pilots got out of it and put it back in a flight idle right away. Everyone's fine. Those aren't the only incidents. There are more.
The most recent incident is just the tip of the iceberg. Investigators uncover 6 other cases where Dash 8 pilots mismanaged the controls of the Pratt & Whitney engines by pulling the power levers into the ground mode mid-flight.
It was pretty obvious to us that inadvertent activation of the power levers into the ground beta range can occur and will occur in the future.
The NTSB has been on top of this for years. They wanted stops on the power levers to prevent movement into ground mode during flight.
What about the FAA?
I asked myself the same question. They followed suit. It was mandated. A lockout system was built for the Dash 8 so this wouldn't happen again.
They fixed the problem.
The design of the system was reviewed, and there had been many changes as to try and make this gate less easy to cross.
They knew about this 10 years ago.
So why didn't Flight 1600 have this system?
Have a look.
This is only in the US.
Exactly.
Dash 8s in the United States had to incorporate a system that prevented propeller overspeed when you went into the ground beta range, and the rest of the world didn't incorporate that system.
If they had mandated this here, it could have saved lives.
Investigators conclude that the power levers of hundreds of Dash 8s around the world have a dangerous flaw. But there is one remaining issue to resolve.
Did we get the results from the manufacturer about what happened to the right engine?
Even though both engines experienced the same overspeed forces, why wasn't the right engine destroyed in the same way the left one was?
Looks like the switch that activates the propellers was improperly maintained.
Shortly after the right propeller oversped, it got stuck in the feathered position and was unable to produce any thrust.
So it's effectively in neutral. It's not in drive, it's not in reverse, it's just going with the airflow.
This prevented the right engine from corn-cobbing like the left one. It's the final piece of the puzzle.
So, Captain Spencer puts the plane in a fast descent.
Investigators finally understand the sequence of events that caused Flight 1600 to crash.
I'm going to take us down.
Copy.
As it heads for Madang, thick clouds are in the plane's path.
The captain wants to see the airport, understandable, but he starts going too fast. Now, around here, at 10,500 feet, the airspeed warnings go off.
Airspeed, mate.
Got it.
He pulls the power levers back, accidentally putting the plane in ground mode.
What have we done?
Both engines malfunction for different reasons, and the plane is now a glider.
It was the worst of cases, the worst of consequences when you've lost both engines, and then you have to do this off-field landing.
How long did it take for them to hit the ground?
The propeller's oversped here, so 4 minutes, 18 seconds.
It's not a lot of time for an emergency landing.
Madang Tower, mayday, mayday, mayday.
But was that enough time to find a safe landing spot?
We needed to know, how did the crew manage the flight? What could they have done? What did they do?
Investigators examine how the pilots of Airlines PNG Flight 1600 reacted after both their engines failed.
What are they doing?
What have we done? I don't know.
Or what were they not doing?
They turn to the transcripts from the cockpit conversation to see if the pilots performed checklists from their quick reference handbook in the final 4 minutes of flight.
When you have both engines out, you're faced with a forced landing, and there is a checklist for forced landing.
Mayday, mayday, mayday. Airlines PNG Flight 1600. We're making an emergency landing.
And the typical forced landing checklist has some basic guidance in terms of what speed they should fly.
Reducing speed gives pilots more time to locate a suitable site and prepare for an emergency landing.
The forced landing checklist would tell them to lower the flaps and put the gear down once they've chosen a site.
But there's no discussion about the checklist.
They weren't running any checklists at all.
Instead of establishing the airplane in a best glide configuration, they increased their descent rate and sacrificed a lot of the altitude that could have been advantageous for them in selecting a forced landing site.
Look there, a river.
The crew reacted, but they didn't seem to do any sort of problem solving in terms of what was the best option. For example, didn't even discuss what speed to fly.
If they configured the plane for a glide, what speed would they have been flying?
Hold on.
The investigators determined the speed the pilots could have slowed to in order to maximize their glide time.
1.3 times stall speed. 2.5 miles per 1,000 feet. That's 120 knots.
When they compare the glide speed to that actual speed of the flight, investigators come to an eye-opening realization.
They were going up to 250 knots after propellers oversped.
Twice as fast as they should have been.
How much longer could the pilots have stayed airborne if they had maintained the recommended glide speed?
They could have bought themselves 6 more minutes of glide time.
That additional time could have come in very handy for several reasons. It would have conserved the energy of the airplane and allowed them to fly longer. It also would have given them more time to perform the appropriate drills and checklists that would have helped them have a more successful outcome from the forced landing.
I'll get as close to the mouth of that river as I can.
Instead of slowing the plane and assessing all his options, the captain tries to get on the ground as quickly as possible.
Following the overspeed, the rate of descent of the airplane increased from 1,500 feet per minute to 6,000 feet per minute. That's a staggering descent rate. The last thing that you would want to do after having lost both your engines is trade away all of your altitude.
With less time to plan for a ditching, the pilots choose a difficult landing site.
Airplanes are designed to take the structural load of landing on a firm surface using the systems that we have on board, like landing gear and flaps. The systems aren't designed in a conventional airplane to land on water.
Boulders!
In the end, boulders prevented any chance of ditching on water. Forced to land on the riverbank, PNG Flight 1600 wasn't properly configured for landing on the ground.
So many people died on this accident. This was an eye-opener and made everybody realize, in fact, something had to be done to prevent this kind of situation.
The investigation into the crash of Airlines PNG Flight 1600 concludes with a clear recommendation.
You can't just say pilot error and be done with it. You have to say, why was the error possible? Why wasn't the error eliminated? In this case, it's the design of the airplane.
A change that has long been made in the United States was not mandated in the rest of the world.
We had enough evidence to be able to force change. We used the power of the pen and the facts and the evidence that we had identifying safety issues, and we presented that to the manufacturer and Transport Canada, and they did change.
A ground beta lockout system is now mandatory in every Dash 8 aircraft worldwide.
It was always a good airplane, but now we've had to make the system so that purposeful act or unintentional act is now safer. I mean, you can't do it anymore if you wanted to.
So in this particular case, we were able to really get down to what had occurred and make those safety improvements. And as an investigator, that's all you can ask for. It's why we do the work that we do. We just want to improve the system and ultimately save lives in the future.